Hello and welcome to Research Matters podcast. I'm your host Badrinarayan and this episode is scripted by Chinta Bhargav Reddy. Today, we will talk about the periodic table which celebrates its 150th anniversary this year. Iron rusts, food is digested, batteries produce electric current, bananas rot, and fireworks burst with color. Many more chemical changes happen around us all the time. Do you wonder what's behind these changes? The periodic table holds some answers. Elements listed on the periodic table combine in particular ratios to form the molecules responsible for these chemical processes. Over the years, many elements have been discovered, taking the tally to 118 as of today. Grouping them based on specific chemical and physical properties makes it convenient to analyze them. In the late 19th century, a Russian chemist named Dmitry Mendeleev recognized this need and proposed the periodic law. It states that when elements are arranged according to their atomic weights, certain properties recur periodically. He arranged 63 elements that were discovered during that time to form the popular version of the periodic table. In 1829, before Mendeleev, Johann Wolfgang Dobereiner, a German chemist, tried to classify the elements. He organized them into groups of 3 with similar properties, so that the atomic weight of the middle element was the arithmetic mean of the other 2. He called those triads, or Dobereiner's triads. For example, lithium with atomic weight 7, sodium with 23, and potassium with 39 formed a triad. Further, John Newlands introduced the concept of octaves in 1864. He found that when elements are arranged in the order of increasing atomic masses, every 8th element has properties similar to the first, just like a musical note. But both these methods had drawbacks. Dobereiner could only apply his concept for 3 such triads of elements, while the elements discovered after Newland's law of octaves didn't fit well. Even Mendeleev's law had its drawbacks. Some elements like argon with atomic weight 39.9, potassium with 58.9, and cobalt with 39.1 have been placed ahead of nickel with atomic weight 58.7. Similarly, the position of isotopes, elements that have different number of neutrons, find no place in the periodic table. The placement of hydrogen was also a problem because with a valency of 1, it can fit in with halogens as well as alkali metals, which puzzled the scientists. In 1913, Henry Moseley, an English physicist, modified Mendeleev's periodic law to address these issues. Moseley proposed to arrange elements as a periodic function of their atomic number, the number of protons in the nucleus of an atom. This system is widely accepted as the properties of elements were repeated after certain regular intervals periodically. The United Nations is celebrating 2019 as the International Year of the Periodic Table of Chemical Elements, marking the 150th anniversary of Dmitry Mendeleev's periodic system. The modern periodic table has 7 rows called periods and 18 columns called groups. The International Union of Pure and Applied Chemistry updates the elements of the periodic table and its compounds. Founded in 1919 and headquartered in California, USA, it monitors the discoveries and inventions of elements around the globe. In the last update, in 2016, it announced the approval of names and symbols for 4 elements: nihonium, moscovium, tennessine, and oganesson. Most of the elements in the periodic table exist in the form of solids and gases. There are very few elements, such as mercury and bromine, that exist as liquids at room temperature. Some elements like carbon, hydrogen, oxygen, nitrogen, and sulfur are involved in making biomolecules essential for life. Californium, discovered in 1950, is the most expensive element in the periodic table, costing a whopping $25 million per gram. The elements in the periodic table after uranium are called transuranic elements. They are made in the laboratory and are discovered through artificial radioactivity, a process through which neutrons, protons, and electrons can be added to convert one element into another. The making of a new element follows a straightforward process. Two simple nucleus or a stable nuclei with charged particles is fused by colliding them with a particle accelerator to form a heavier nucleus. For example, fast-moving particles such as neutrons collide with uranium nucleus with the atomic number 92 and generate neptunium as an intermediate element which has an atomic number of 93. The neptunium formed in this process has an unstable nucleus that undergoes further reaction to give plutonium with atomic number 94. Plutonium is very stable and has a lifetime of 24,000 years. Now comes the question, are there only 118 elements? Is oganesson the last element, or is there any possibility of finding more elements? This brings us to the expansion of the periodic table. At the moment, scientists around the world are on the hunt to find the elements 119 and 120. In December 2017, at the third symposium on super heavy elements conference held in Poland, Hideto Ennyo, director of RIKEN, a research and development institution in Japan, announced that they would make the elements 119 and 120 within 5 years. Like Japan, researchers from various research institutes across the globe, mainly the US, Germany, Russia, China, India, Great Britain, Switzerland, and France are trying to find the next elements with their respective collaborators. Thank you for listening. We will be back soon with another episode. This podcast was brought to you by Research Matters, a SciComm initiative by Kubi Labs. For more such podcasts and science news, log on to www.researchmatters.in. Until next time, stay tuned.